Okay, good afternoon, everyone, once again. So today we are going to do more of hands-on. We've already kind of gone through embeddings and how we can use embedding models to get embeddings, right? So the next thing we are going to do now is to pull that knowledge together with what we've done so far and build the RAG, the Retrieval Augmented Generative System. So in order to build a Retrieval Augmented Generative System, we need to have our own database, vector database, where we will store the proprietary information that you want, the additional context that you want to send to the LLM. So we are going to look at the vector databases. This is more or less a recap from last Wednesday. So remember that a vector database is a specialized database that is optimized for storing embeddings, right? Embeddings of obviously the embeddings are the representation of the meanings of concepts that the LLM is dealing with, right? So an embedding is basically a representation of a concept. And this embedding is actually represented by a sequence of numbers. It is this sequence of numbers that we call a vector, right? And this sequence of numbers is normally stored as a list or an array in most languages, right? In fact, in all languages, whatever data structure that you use to represent a list or an array, right? That's what we use to store the RAG. So, sorry, the vector. So the now vectors are basically, like I said, a long list of numbers that can be as much as 300, 700 and something, right? Different numbers. So you want to use this as an index, right? To store the data in your database. You're using it as an index. Okay, so think of it like, what I mean by an index is, for those who are familiar with the way databases traditionally, how they work, you have what we call a key, a primary key, right? So um, the primary key is what allows you to keep track, of the information. So each record or row in a database will have its own primary key, right? That's what the primary key is, basically. So when you take a row of data, you store it. When you are storing it, you make sure that it has a primary key. So a primary key is a kind of index. It's basically you may call it an identifier, right, for a particular row or record in the database. And that identifier, that row has additional information. So it has columns. The columns contain additional information. So for example, if you were storing people's profile information in the database, a row will contain, the record for a single user. And for that single user, you would have the primary key. You would have then the first name as, one of the fields or one of the columns. You have the last name. You have maybe date of birth. You have, bunch of other things, origin, a bunch of other things, right? So all of those things are in a single row and are associated with that single user. So anytime I want to retrieve that user, I will use the primary key. But of course, databases give you more flexibility than just using a primary key. You can also use the first name. You can search, so you run an SQL query, SQL query, and you specify what we call a where clause. A where clause is basically a condition or a filter that you use to bring out the rows or the records that match a particular condition, right? That's how a regular standard database, behaves, right? Generally. Now, with vector databases, right, you may still have a primary key, you will have a primary key, but in addition to that, a vector database allows you to add what we call the vector. That's why they're called vector databases. That's the embedding, that list of numbers, that string or sequence of numbers, so you can store it as well. And you can use that as an index or as a key to identify the rest of the information that you have stored in the database for that specific record or row. So for you now, if I use that same, example I used earlier, if we are storing a record of a single user, right? Yes, we had the primary key, which is a user ID. Then we had other things, first name, last name, date of birth, and all of those other things. For a vector database, it allows you to also add a column called vector. Well, not necessarily called vector, but it's a column that contains a vector, right? So that vector is what makes the difference. And what makes vector databases, different from regular databases is that it is optimized so you can do all kinds of manipulations of that vector. It's just like for GIS, for example, for those who may have done a bit of mapping systems, there is a library in most databases that have GIS, geographic information systems. Those ones are for mapping. So those ones are also optimized. Well, not the database itself, but the plugin or extension, the extension that you add to the database allows you to be able to calculate things like distances between 2 points, right? So you can actually search in the database and retrieve, records where, the map column or the coordinate column, there's always, a coordinate system, latitude, longitude, right? Where that coordinate system matches a certain radius, So that's basically the same thing, right? With vector databases, coordinate system is just two numbers, the latitude and the longitude, right? 2 dimensions. But in a vector database, you now have more than just two. You have 300 and something, 700 and something. That's the number of numbers in that. So it's optimized to be able to basically, manipulate that information. And what are the kinds of operations or manipulations can you do with the vectors in the vector database? You can do search and say, okay, find the vector that matches this one, right? But considering that they may not always be perfect matches, right? You can say find vectors that are close to this one. Just like in the GIS database, you say find the points that are within the same radius or within a certain radius of this point, right? You can also say, okay, find vectors that are close based on the similarity score. And you can define which similarity score you want to use. We had looked at it before, we have the cosine similarity score and we have the dot product similarity score. So that's what vector databases are, right? Compared to the traditional SQL or NoSQL databases, right? So they're not optimized. Those ones are not optimized for high dimensional, but vectors are high dimensional vector operations, fast similarity, and lots of vectors. So these are some of the features which you would look at and you would see indexing based on similarity score is much, much faster for those vectors. High dimensional vector support. So you can see some of them support 384, numbers in the vector, all the way up to 4096 dimensions or numbers in the vector. It has additional metadata filters. So the additional filters, which like what the basic usual SQL databases would be able to do, they can also do it, right? Hybrid search. So hybrid search is where you can combine both the vector and the keyword. The keyword is what a regular database would do, but you can also combine key vectors with these keywords, and it still can do those searches. Scalability, it can scale to large numbers of entries with large amounts of vectors, and it can still do all of this search, for this large amount of vectors. Persistence, yeah, you can store vectors safely. It also supports versioning, so you can update documents and keep version numbers. So what that means is you probably can also get older versions. And then, of course, the RAG integration. So we looked at that last week, and we looked at the three of them that are really kind of like the top players. Okay. So you see that we have the Pinecone, we have the Chroma DB, and we have the Facebook AI similarity search. Pinecone is cloud-based, so I'm going to show you how you get a Pinecone account, and then you can create a database, and then you can add things into it. Same thing, Chroma DB, right? Chroma DB is open source, so you can download it and have it locally. Okay, you can easily embed it in your apps. It's good for prototyping, and it works well with LangChain and Llama Index. We're going to look at LangChain later on. LangChain will help you to really speed up your prompt chains, basically. So it makes writing chains so much easier. Then Spice, which is a Facebook AI similarity search. So this is not really a database, but it's a library, which allows to parallelize these operations very fast using SIMD. SIMD is single instruction, multiple data. It's basically a technology you use with GPUs to speed up. Basically, it does things in parallel. It's highly parallel operations. And in this kind of context, yes, you do need highly parallel operations. So for files, you need to build your own database around it. So you need to have a database, and then it will access the database, and then it will do all of the vectorized stuff in that database. So, and this was the last slide we looked at last week, where you look at the steps to making up a RAG. We are going to come back into this slide, but first, I want us to just go check out Pinecone. So you just search for Pinecone, right? You will see pinecone.io. This is it. So you sign up and create an account. That's how simple it is. They have a free tier. Okay, so I'm going to sign up quickly. So this is very easy. Once you put in your email, and you click on this, right? They will send you a code. Once they send you a code, you find your email, and you get the code. And then once you get the code, of course, you have access. And it's as simple as that, right? You put in the code and you have access. Okay. So once you do this, right, this is what you get. You get this page that says, I'm building a smaller personal project. I'm building for scale or commercial use. So for now, I'll take this option. I guess this would probably be a standard trial, but I'll take this. And then what are you building? Exploring search, RAG agents, recommendations. Okay, so let's just say RAG, right? What kind of data do you have? Vector embeddings, raw files. Um, well, okay, so I don't have vector embeddings yet. I just have raw files. So let's assume I have raw files. How will you build your solutions? AI assisted development, manual coding, um, no code, low code. So I'll use working directly with SDKs, CLIs, or APIs. So let's say AI assisted, all right? And what coding? What coding? Which AI coding assistant are you using? So I'll pick Copilot. Can't see the rest of the screen.
So I think you can skip this process. So look at skip publishing.
Oh yeah, well that's a good point. Can't even see the rest of it to click. So, but anyway, you get here, an API key is generated. So I'm just going to copy this API key and close. So you have this as your interface. And that's it, right? Now let's just try a few things. So I guess so you first of all start up, you have database. So that means you already have a default database, right? And then you see the indexes, backups, assistant. Now the assistant really helps, right? So maybe we can just go with the assistant and see to speed things up. Okay. Um, so you have a create assistant endpoint if you want to do it from the endpoint. Getting started. So let's go to get started. So it's actually easy for you to just create this, right? From pinecone, import pinecone. And I'm going to do this on a Jupyter notebook. I don't know if this works with other languages because it does look like this is, but I'm sure if you go check their docs, so let's go look at their documentation. You should be able to, I'm sure there are ways you can integrate with other languages. So you can use JavaScript, for example, to run your queries and still call the API and push your vectors and everything in there, right? So I would, and we're actually going to do something with JavaScript as well. So we'll see how we do this with JavaScript. But if you're not too worried about which programming language, you import this, right? And then you call Pinecone, you create Pinecone with the API key, right? And then you can now begin your setup. So you first configure and create an index, okay? Then, so the index is the whole deal, right? The index, that is what makes a vector database, right? So we can, you give the index a name. So maybe something like, let's just call it embedding. You can call it anything. there are other configurations you can use, right? So the interesting thing is that this allows you to configure custom settings based on different um, embedding APIs or embedding models because it depends on the embedding model. But if you look at this, right, this index is configured for Llama text embed version 2. So you will see this information that you need to use to configure it. The modality is text. So modality is whether it's multimodal or not, right? So text means it only handles text. The vector type is dense. It's not a sparse vector. A sparse vector is a vector that has a lot of zeros in it, right? Than actual numbers. A dense vector is a vector that has a lot of, actual numbers. The maximum input, this is the maximum number of tokens that is expected to come in, 2048 tokens. The starter limit is 5 million tokens. The dimension is 1024. That is 1024 is the size of the vector or the size of the embedding, right? It's 1024. And the metric, how you are measuring similarity is cosine. Okay. So you can do that. I chose Llama text embed, so it gives me this configuration. If I choose this second one, it gives me a different configuration for a Microsoft hosted embedding model, the multilingual E5 large. So you can click on this to see the inference API, right? Well, it's not clickable, but it tells you that it's an inference API. Basically, it's hosted. This one is NVIDIA hosted, but it's a Llama model. Then Pinecone itself has, Pinecone hosted sparse English. This is a sparse model. It's a sparse model. So like I said, sparse model a sparse vector is a model that generates a sparse vector. So a sparse vector is a vector that has a lot of zeros, a lot more zeros than actual numbers. So you can see that for each of these, you have slightly different configuration. You have the modality again, text. Vector type is sparse. Max input is 512 tokens. Data limit is not available. And the metric for similarity calculation is dot product. That's the Pinecone. This one is multilingual E5. So text vector type is dense. Max input is 507 tokens. Starter limit is 5 million. Dimension is 1024. This metric here, cosine, is interesting. This one you could actually choose. So maybe there are different ones. So we can look at the other ones as well. This is OpenAI text embedding 3. So this is OpenAI's most powerful embedding model. So again, it gives you text modality, dense vectors, 8,191 tokens. Dimension, you can choose up to 3,072. That's the size of the embedding vector. And 256, And then you can choose between cosine and dot product as a metric for this one. Then for this one, text embedding 3, small. This is the most cost-effective OpenAI embedding model, right? This one is a bit smaller embedding, and but it still gives you the same thing as this other one, right? But it gives you 512, it gives you 1,536. This one actually gives you both either also. So hang on, I think I missed something. Let me go back. Okay, this is if you're using a custom. So let's go back to the non-custom. I was trying to compare text embedding 3 small that gives you 1024 and this one that gives you 512. So this gives you 1024 but you can go up to 3072. This one also gives you 512, and you can go up to 1536. So, yeah, or you can just go do your own manual configuration, which is either click here or click on this checkbox here. So if you click on this checkbox, it allows you to just choose. If you already know what embedding um, configuration that you're going to have, you can type it in. Even the dimensions you can type. So of course, the bigger the dimension of your vector, the larger the size of the database per entry. Then you have cosines, capacity, and all of that. Or you could use cloud providers. Okay, so let's just take, I guess the benefit of using these ones would be field map is text. So the benefit of using this pre-configured one is you can actually allow Pinecone to do your embedding conversion yourself itself, right? Because if you do a custom thing, that means you have to run the code that will do the embedding conversion, right? Which is still okay. And I think maybe we'll go with that approach first, right? But here is the reason why we're going with all of this is once you specify this, then you don't need to actually send Pinecone embeddings. You send Pinecone the text, right? And then Pinecone will run the embedding through this, because you have already chosen the embedding provider, right? The embedding model. So it's going to run it through this, through either the NVIDIA, these are all hosted and these are all free, right? So Pinecone basically will use them to generate embeddings and then do its storage. But in order for us to really understand how things work, I would like to go with the custom configuration. We're going to use a dense, and I'll use a small dimension. So now we have to decide which embedding model we are going to use, right? Because I want to go through. So let's say I go to Hugging Face. I'm going to go to Hugging Face. You could also try Grok. I did show us Grok. Grok is also a host. Grok, by the way, does not provide models. Rather, Grok provides, you know, compute. It provides uh, the compute infrastructure for you to either host your models and do stuff. So it actually does host a lot of models, right? So you can go get an API key. I think I had one already. I had already created an account. So you can get an API key, and then you can, it has a playground. It has, so you basically can access Grok this way. Same way we've been accessing all the others. You do an API call, you can use the OpenAI client, where you pass in a Grok API key, and then you pass in a Grok endpoint, right? So it has a bunch of embedding. So let's see, I'm looking for embedding. Well, let me go to Hugging Face. Hugging Face has embedding models. So let's just go. We'll filter by embedding. So we have a bunch of embedding. So I think we'll just go with this. Now, I want to try and see if this gives me what I want. So I'm going to create a new, okay, I think I had created one already. I'm going to create a new Jupyter notebook. I want to do this on a notebook. You could also do this on VS Code as well, right? So it's the same thing. But I like using Colab notebooks because it basically makes things really fast for me. I don't have to do too much setup. but the same principle applies everywhere, right? The only thing is that if you're doing it in your VS Code, you do have to first of all um, install all the dependencies and all of that. Okay, so um, so um, let's start with Hugging Face. So to get the okay, so Hugging Face has a sentence transformer. So a sentence transformer, you can create a new sentence transformer for embeddings. All right. Now I'm going to go get this. We could just go with this sentence transformer. What I did was this, I just typed sentence transformer. All right. Okay, I started off by typing embedding and it gave me this and it still allows me to do like um I can I can use this to filter the search. But at the end of the day, I have this. So I want to use this Google embedding gem because it's classified under sentence transformer. So I'm going to click here to copy the this name, right? This name of the model. So I'll copy it and then I'll go to this and I will paste that. So the first thing I want to do is just to be sure that this works properly. So I'll run this. So once I run this, if I don't get any errors, then it means that I got my name correctly. This is very important. Sometimes you probably just type a name. Sometimes you use a namespace, Google/embedding Java. So while that is running, um, this helps us to do embeddings, right? So the next thing we will do is let's create an embedding of a single. Oh yeah, I do need to add the Hugging Face token. So let me create a .m file. Uh, so I should have done this earlier, but I can do this quickly. So I'm going to just quickly um, so I have Hugging Face API key. Of course, for it to pick up that, um, I did not specify the API key. So let me first of all specify the API key. And then let me import .m from .m import load and then I'm going to load the .m. Okay, let's see if this works now. So It says that the model is restricted. I must have access to it and be authenticated. So I think I still am not properly authenticated. So um, let me just confirm that my .env is picking up. HF, because typically that's the name that we give for Hugging Face. But if that is not possible, then we will go use another embedding model, right? So HF API key, HF API key. So I want to check that this is working well. So I'm going to run all of this again. Okay, so we got this time. So let's see again. So it's still giving me the same error. So I assume that it is not directly accessible. So I'm going to use a different one. I'm going to use this. So let's use the all mini. The all mini is going to give me what I need. Yeah. So I get this from all mini. Okay. So this is the so I got an embedding model now. So I can now look at the embedding, and normally you say, okay, let's see how this looks like. So I can say model dot encode. This is a sentence. Let's put it this way, vector or embedding, or whatever I want to call it. So this vector shape, I want to see its dimensions. The dimensions is what I need. So it's 384. I can also show the values, right, as well. So maybe I can check for the first 10, elements in it. So 1, 2, 3. So you can see this is not a sparse vector. It doesn't have a lot of zeros in it. So it's a dense vector, right? So this already gives me two of the metrics I need. This is the vector size and the sparsity. So I can go back to the pine cone. The dimension, remember the dimension is 384. So we have 384. I could choose whichever metric, cosine or dot product. It's a dense, right? So those are the three things. Capacity mode, serverless, charges based on data storage reads and writes. So this actually uses AWS. So I can also choose a cloud provider. So Pinecone basically is leveraging on existing cloud services, AWS, Google Cloud, or the Azure. So region. Okay. And with that, you can also do deletion protection, right? This means that it makes it hard for people to mistakenly delete entries in that database. So I can click on create index and right. So I've created the index now. And you can now check to see we don't have anything in here. We have browser metrics, right? Namespaces, configuration. Okay. So I've created an index. So that's the first thing, right? You create an index. Now, the next step is after creating the index, right? You can now load some sample data. So of course, remember you have to be able to connect. So let me pull this piece of code into my Jupyter notebook as well. So if I want to, I will do this, right? Um, so you load sample data, that's the next thing, right? So to load sample data, this is a good example of sample data, right? Um, from their data sets, that contains blockbuster movies. This is the first step. If you want to continue with this, you can, this is more or less like, example of how you can do it. So maybe we can try the examples, right? Or you can check the example notebooks. But typically, you take this sample data, right? Then you create vector embeddings, right? Then you create an index, which I have already done, and then you offset. It's as simple as that. Offset records. You put records in, right? And then when you want to do a query, you create a query vector and then you query your index. That's as simple as it is. So let's just do this. So you can create vector embeddings. Here, it's actually to create the vector embeddings, right? So using our own example here, I already have a pine cone, right? So I can now create. Um, Now let me check first if Pinecone exists. It doesn't exist, so you have to install it. So in my um, notebook, I will simply install Pinecone client, right? Pip install Pinecone client. So it will install that. Once it installs, then this is available. Then I'm going to put in my Pinecone key here. So I'll use os dot get environment variable. Pinecone API key. So I'm going to also add this API key to my .env, to my environment variables. And I remember I had copied it. So remember, you can get API keys from here. Click on the API keys. I already had an API key. Okay, I can't remember where I saved, where I pasted it. So let me create a new one. All right. All right. So I'm going to copy this and I will paste it here. So I now have that in my .env. So if I run, I'll run everything again. So I get to this point, requirements already satisfied, right? Um, okay, so I should call it Pinecone. Yeah, so it looks like there's a conflict between Pinecone client and Pinecone. So I'm basically going to rerun the notebook. Okay, so for Hugging Face, we need to call it HF token, not API key. Um, Yes, we need to call it API token. So I'm going to restart session and rerun this. Okay, so we have this model. It's available. So we've encoded the basic, we've installed Pinecone and we've initialized Pinecone. So the next thing we will do is so we've loaded sample data. So the next thing we'll do is run embedding. Okay, so we'll run the embedding. We've already run embedding, so we already have a vector. So now the next thing is to store it in the database. Okay. So you create a record, right? This is how you create a record with Pinecone. And I'm going to bring this up here. So basically, a record contains ID values and metadata. Okay, so this is how it looks like. Okay, so this is how it looks like. You have ID, you have values. The values contains a stringified version of your vector, the embedding vector, right? So it should be, you turn into a JSON string basically, and you pass it in. The metadata will now be the additional information that you want to store, related to this. So basically it's going to be the embedding of whatever it is, right? And that metadata is typically passed as a dictionary, an object basically that has name and values, okay? And that's it. So once you do that, then you can just go and call the offset method. Okay, so let's do that here. So you can say the record equals, all right, it's ID. Okay, then the values will be a vector. It should really be to string. Then the metadata. You can say text. So I'm just using text. So remember what was the text that we were actually encoding? This text. So that's the same thing because you want to say, okay, if I'm trying to search, I want to search for this, right? So, okay, that's the record. So you create the record and then you put the record into the database. That's it. You put it into the database. So, to do that, Pinecone has a function that allows you to put stuff. So use the offset function. Okay. So first of all, we have created Pinecone PC, right? So PC is a Pinecone instance. You can now retrieve the index. Remember, we have created an index. So the index was called what? Embedding. So to get the index, you use pc.index. Then you specify the name of the index. We call the index embedding. right? This will give us, this will connect to the Pinecone API and allow you to access that index and do stuff with it. So you have this index. Then I can just offset stuff, right? And a simple way to offset is index.offset. Offset is basically like insert. And then you specify the vectors. So remember we have that record there. So we can say vectors, okay. So the vectors will be basically a list of all the records that you want to put, right? That's vectors. It's going to be, so since we are putting only one record, right? We will just put that record in an array and we offset it. Then when I run that, you now get an offset response, meaning that you have successfully loaded it. If you now go back to Pinecone and go check the index, so you go back to your database, you check your indexes, you'll see that embedding, you see the embedding here, we connect to it. You can now go to the browser, you now see that I have created a record. You can see that there's a record now, which we created, right? So with the API call, we were able to add it. The ID is 0, the text, this is a sentence, right? The vector is there, it is not shown to us. You even have a score here, okay? So that's basically how you start, you offset. Yes, Ginika, go ahead with your question.
Okay, thank you, sir. Please, I have like multiple questions. Let me start with the first one is about the dimension. When getting the dimension, do we have to run that Hugging Face model first to get the dimension before we can now create our own
Yes,
custom?
yes, because you need to know the size of, if you are creating custom, you need to know the size of the vectors that you'll be putting in there. So you have to run it. Now, it's possible that you could put multiple embeddings that have different sizes. And I know there might be that question, but I don't think I recommend that. I don't recommend that because the whole thing, the whole essence of embedding is that there's meaning associated with it. So you have to be consistent in which embedding model you use. Whatever project that you are using, right? You use the same embedding model. Just think of it like um, I don't know what example to use. Like if you are using a particular translator to translate, right, into a particular language. In fact, think of an embedding as the meaning of something in another language, right? That language is the language that the LLMs understand. You have to use the same language for all of them. In a particular project, in a particular vector database. In other words, if you use different embedding models to generate embedding, and you put all of them in the same vector database, it doesn't make any sense because those embeddings are not from the same language inputs. They're not from the same space. So they don't have the same meaning. The meanings don't correlate. Even if the dimensions are the same, the meanings don't correlate. So one of the rules is that you always need to keep the same embedding vector. Always need to use, the same embedding model to generate your embedding vectors. If you use a different embedding model later on, right, everything everything will get messed up. So the next question you might ask is, okay, what if maybe I have already done a project and I want to upgrade the embedding vector to something else? What do I do? You have to run embedding, you have to rerun embedding on every single row in that database and offset with the value of the new vector. You understand? So that's why now a database like Pinecone gives you the other one where you can choose which model you want to use. So in that case, you are not the one manually generating the embedding vectors. You can just send clear text to Pinecone and Pinecone will still generate the embedding vectors for you. Okay.
Okay, sir. This 384, is it the size for Hugging Face embedder or is
Is
it
the
the size
size
for?
for this specific, not just Hugging Face, right? On Hugging Face, you have a lot of embedding models that are hosted there, right? But for this specific all mini LM L6 v2, right?
Okay.
Which you can go to Hugging Face and search for it. I just copied and pasted it here, right? Sentence transformers, all mini LM L6 v2, right? In fact, you don't even need to run it. If you come here, you will see it will give you information on it. So for example, it should be able to tell you the size of the embedding. So this is how you use it.
Sir, it's written there. If you go to the top, you see where it is
Yeah,
written.
I think I missed it because I was looking for it. All mini LML6
You see where it's
V2.
written. This is a sentence transformer model. It maps sentences and paragraphs to a.
Okay, there it is. So I missed it, right? So you should be able to get the vector size, the embedding vector size from here. 384 dimensional dense vector. So you can also see it's a dense vector, right? So
Okay.
you don't really actually need to run it. You can just come and check it here. But sometimes I like to be very sure of myself, so I'll run it first and get an embedding from that model and use that value. Okay.
Okay, sir. For practice, which will you recommend? The custom one or the already
The
made one
custom one
like
is better because the custom one exposes you to everything. You configure everything yourself, so you understand it. Then this one, all this one does, right? If you go to this second approach, where, sorry, if you go to this, right, where you want to create, and you are choosing this, all it does is that it will still create and it will automatically load this information for you. But the only thing is that because you have used a model that Pinecone knows about, it's not going to, you can just send it clear text. It will run the embedding by itself, right? Because there's an inference API that it will be able to call and get that embedding. So that's why it says integrated embedding new. Like let Pinecone manage the conversion to vector embeddings when you offset and search. So you don't need to do the conversion by yourself outside of Pinecone. Pinecone will do the conversion and use the embeddings from that conversion to do the search or any offset. You get. So with this, you
yes, sir.
can actually send real text to Pinecone and ask it, okay, search for text that matches this thing I'm saying. Okay. So they basically just take it. This is for people that, yeah, this is cool, right? As well. But you as a developer, you want to be able to know how everything works under the hood. So after you've practiced with custom settings, you can still come and try these ones as well.
Okay,
Okay.
sir. The second question um is okay, I don't know, sir. This the documentation because I saw you ran it so that you can know the model, whether it's dense or sparse. I don't know, is it also written in the documentation if it's dense or sparse, the vector?
Yeah, but
Because you ran it also.
I just showed you that here. Can you see this?
Okay, okay, okay,
Three
okay,
eight
okay, sir.
four dimensional dense vector.
Okay,
Okay.
sir. All right. The other one was on the JSON file that you copied on the Google Colab.
Mhm. That's just the API. That's just how you create, right? An example. So for Pinecone, you have to create a record first before you offset it, right?
Okay,
And to
like my
create a
question
record,
is the the um the JSONs were kind of different, and because me I thought that
is that's
it
not
has to be
JSON,
the same.
that's a Python dictionary actually.
Okay, sorry, the dictionary was, I don't know if that is an example that they gave,
It's an
because I
example.
saw that you did your own.
Yeah, it's an example. So I was just taking it from there, just um to be sure, right, that I'm not missing anything, you know. It's always good to
Okay,
check documentation and confirm. So
right.
Basically, it's taken from their documentation. Okay. All right. So I am now going to write a quick function that will create an offset, embeddings for me, right? So I start off with these 5 sentences, right? The 5 sentences, I have already prepared them. So in fact, we used them in a previous class. So these 5 sentences. So for each of these sentences, I want to offset. So I'll do for sentence in sentences, right? So of course, my thing has done it very well. So vector is model.encode. So you first of all encode the sentence into a vector. You create a record from it, right? ID, it uses UUID. I don't know if that's going to work, but maybe I can just import UUID. All right. Then after doing this, I'll now do index offset, right? As a matter of fact, you can do it better. You create all the records at once because it's an API call. It makes more sense, right? To accumulate it, right? You create a list of records. So let me show you how this will look like after I've created the list of records. So remember, like what you're asking me, this is how a record would look like that Pinecone accepts. This is like their convention. Okay. So you now record ID. So you give it an ID, which I generated this ID using UUID4, which is just a function. Then values, you convert this vector to list, basically. Then metadata, right? And you record it. So this is how records will look like. Of course, it is it is dominated by the vectors. The vectors are plenty, but let's see. Yeah, so you see this. You have the metadata, that's the text, ID, values, and metadata. So that's how the record looks like. So we now pinecone the index rather, index.offset, and that's it. So you run this. I have now offsetted count 7. So it tells you have basically added 7. And do you know why it's called offset? Why it's called offset is if the vector matches exactly with a pre-existing vector that you already have the database, it's not going to create a new entry, right? It's going to replace it. So now if I go back to my pinecone and I look at indexes, right? I go to this one. I go to the browser. You will now see that I have more of these records which I added. So you see the ID, which is the UUID that was generated. This one had 0 because I just typed it in. And you have this. And you now see we have score. So score, um, similarity score kind of. So it's already generating score for you, which you could use, right? So that's basically how you can do it. Now, to do stuff like searching, okay, to do stuff like searching, um, so now let's do an interesting thing. So if you want to do a query, right? Because a query is what really matters in in all of this, right? So let's assume I want to find the sentence that is closest. I've put in a lot of sentences, right? But I now want a sentence that matches maybe this artificial intelligence, for example. Or so let's say I want to find matches, okay? So the candidate or the thing I want to match is let's say text equals I am happy to be studying AI, right? So the first thing we'll do is we'll create an embedding, yeah, a query vector, a text vector, whatever, a vector or embedding for this. So we'll still use our, remember the model you use to create the vector that you store in the database, the same model you have to use to encode the text that you want to search, right? Then after that, once you have encoded it, you can then go to Pinecone and say index.query, right? As simple as that, index.query. Now you specify the query that you want to, which is this embedding. Then top K means top how many, right? Top how many. So if I say top K equals to 3, it's going to give me the top 3 matches, right? If I say top K equals to 5, it's going to give me top 5 matches, right? So let's run this now. So you can see it gives you query responses, right? It gives you the matches. So if you go look at the matches, right? So let's call this response, okay? So we now say response.matches. Let's look at the matches. You see that we have 1, 2, 3, 4, 5. Right? And we say the top 5. So we have one that has a score of 0 0.432, 0 0.2439, 0 0.2300, right? 0 0.1364. Now you have this, okay? But the question is, how do I know what are the things that matched this? So you can also add another argument here. That argument says include metadata, right? And you say yes, true, okay? It will now include the metadata when it's retrieving. So let's now see the matches. You now see the metadata here, text, artificial intelligence transforming industry. This is the highest, this is the best match with this score, right? Because I said, I'm happy to be studying AI. So it matches the one that has AI. Can you see? Then the next match, which isn't the very as high of a score, is 0.2439, the matching score. It tells you that deep learning models use neural networks. And then I am cooking rice is also a high score because of the I am, right? But can you see that if you were using a normal matching, maybe I am would have been the highest because that's the one that has I am. This one has I am as well. But it understands the meaning of what you are saying. So I am happy to study. It knows it's AI, right? So it picks the one that is talking about AI as the closest match. I am cooking rice is number 3 because even though it's not talking about AI, but it has I am in it. This is a sentence, I bought a new car, right? So that's the top 5. So with this, now the next thing would be if you were trying to get information for an LLM, you can then take this metadata and then add it as context. So if you had already had a prompt, right, you can now add to that prompt, you can add the highest score from this, right? Response dot matches, right? 0. Matches 0 is the one with the highest score. Dot metadata, or it shouldn't be metadata, is metadata, right? And text. Okay. So let's say prompt context. So this will now be the context that you add to your prompt. And that is basically how you enhance. So that's the augmentation part, and the retrieval part with Python. Okay. So I don't have a lot of time left because I wanted us to do a bit of RAG. Now considering where we are, I don't know if, but the other one I wanted us to look at was the ChromaDB. So ChromaDB is nice because you can basically do it, you can install it locally, okay, on your computer. So because at the end of the day, a lot of these things, you have to be able to run them locally on your computer. So let's see how we can do that. I haven't shown us yet how you can run an LLM locally, by the way. So, but we will look at that later on. So we can combine all of this. But I just wanted us to get all of these concepts in place and understand. Okay. Now, for ChromaDB, it's again not difficult, right? For ChromaDB, you basically just run this is how ChromaDB does its own bit. So I'm just going to show you this. I would like you to go and experiment on your own because we don't have that much time. So I'd like you to go and experiment ChromaDB on your own. But ChromaDB, you have to install it locally. So let me open the, let's look at our existing project. So we are going to look at our project in VS Code, right? So I'm opening it up, so give me a second. So this is my VS Code interface. So here I want to open up a project. All right. So we have it's open now. So I'm going to create a new folder and I'll call it ChromaDB rag. Right. So in ChromaDB, so the first thing you do is your terminal. You have to install it first, right? You have to install it first. So I'm going to create a virtual environment in here, right? So remember with Python, I'm still doing Python, but you can do the same thing, you know, for any other programming language. So you would, let's create a Python virtual environment first. Okay, let's do this in ChromaDB. Okay, so I create a virtual environment, then I source the virtual environment, activate. Or if you're using Windows, it will be VM script activate.exe. So once I do this, I can then pip install ChromaDB. It's as simple as that. You pip install ChromaDB. Okay. So this will take a bit of time. So while that is downloading, I'm going to switch back here. We're not going to look at the Facebook one, right? But I would encourage everyone to go to a bit of research. So while this is downloading, because this will take a bit of time, I'm going to switch us back. Yes, go ahead.
So you said if you're using VN, what should we do?
We are using
VN. Central network.
I
Do you
didn't
get my
understand
point?
the question.
Okay.
I didn't get the question.
So you said when we're using VN in installing this, what should we do?
Virtual environment,
Yes.
VNV.
Yes.
Is pip install. Once you've gotten into the virtual environment, you pip install. That's what I'm doing currently. Pip install ChromaDB. ChromaDB has a hosted version, right? Pinecone is ChromaDB has allows you to do local installation, while Pinecone is a cloud version. So because ChromaDB allows you to do local, you can, that's what I want to show here, that you can install it locally and use it locally, right? Versus Pinecone that you have to create an account in the cloud. Okay.
Thank you, sir.
Okay, so while this is downloading, let me now show you. This is going to take of time because there's a lot of stuff, right? So let's continue. We'll come back to ChromaDB later on. So if you are doing RAG, we're going to go through just implementing a simple RAG, right? Very simple RAG. So I remember I mentioned this 6 steps, right? Step 1, chunk your data, split the text into sections, right? Step 2, generate embeddings, which is creating embeddings for each chunk. Step 3, store in vector database. So we have effectively done these 3 things, right? The only difference is that I did not chunk the data from the beginning, right? What I did was I already had like 3 or 4 sentences. Of course, in real life, you are not going to be doing 3 or 4 sentences. It's not sentences. It's entire documents, right, that you will do. Generate embeddings, we did that already, right? You just get an embedding model, whether it's on the cloud or whether it's the one that you have locally running, okay? And then you call that model and ask it to encode and give you the embedding. Store in the vector database, we just did that. We stored the vector and the metadata. The metadata will contain a bunch of additional information, including meanings or context or just what you are even encoding, right? An additional thing. Then after that, when your user runs a query on the RAG, right, what you will do is take the query that the user has made, like I just did now, right? I love AI or I am learning AI. You convert that user's query into an embedding, just like I did, and then you run a query on the vector database and ask for the top K documents. And you see, I did a top K of 5, right? So you get the top 5 records. Those top 5 records, you can now extract the information you had stored in the metadata, right? You now extract that information and you add it, attach it to the prompt, okay, that the user has done. as context, or you can even send it as developer context or admin context, but I think it's better to add it as a user context, right? And then send that entire thing into the LLM. And then the LLM will be able to look at all that context and come up with a very good response. Okay, that's just the process. So of this 6 steps process, I have already done step 2, step 3, step 4, right? Step 5. Okay, step 4 is a user query. Well, I simulated that. Step 2, step 3, step 4, step 5. So feeding into LLM, well, we did all of that when we're doing prompt chaining and all of that, right? So at the end of the day, it becomes very easy. So let's just, we're going to see how we can do this very simply. Okay. So I'll keep this pine cone so we can see how pine cone works. Now, if we want to do a RAG, right? We want to do a RAG. So I have here, a little notebook I had put together. So when you are doing a RAG, one of the things you really be thinking about is what they call the architecture, right? So the RAG system will augment the LLM. We already know that. Indexing your data into a vector store, we just saw how to do that with Pinecone. Retrieving relative chunks at query time. We also saw how we can just query based on a prompt from the user. Feed those chunks to the LLM alongside the user query, right? We just saw how to do that. And let the LLM reason with that additional context. So, but this is the first step. I already gave you like 6 or 7 steps. The first step is the raw data. Now you can do data cleaning on it and normalization, which is like the standard process when you are dealing with data, right? Then chunking. Chunking is very important. And there's what we call chunking strategy. I'm actually going to share with everyone a video that you can watch that will give you very, all of the details in a compressed form, right? But chunking strategy is very important, right? And when we are talking about chunking strategy, right? What do we mean exactly? Chunking strategy is basically how are you putting your things together, right? How are you putting your stuff together? How are you putting your rather how are you splitting them apart? Do you split them so that they will have overlaps, right? Or do you split them in such a way that you know the there is no overlaps? What extent of overlap should you have when you are doing this chunking, right? Or do you just have them clean? Because overlaps are important. And what do I mean by overlap? So let's assume that you have a long document, right? So let me look for a long sample document that we can use for this example. Um, okay, so I'm going to get some sample documents. So anyway, so while we're getting that, so we have chunking, right? Then after chunking, we have the embedding generation, which is very important. And then we have the vector store index, which you have to create, right? Vector store index, we just created that. Then we have what we call the retrieval pipeline. So the retrieval pipeline is going to basically automate the process of retrieving based on user prompts, right? And then we have the context construction, which comes from the data that you get from the vector database, right? And then you know, pull it together with the context and then you generate. So the first step in this is collecting the data. So the data could be files, PDF files, HTML files, Markdown, JSON, or whatever kind of data that you have, right? Now, you should be able to extract text with that, with a text extractor, okay? Then, so for example, if the document is a PDF, you should be able to extract the text in the PDF, right? If it's a HTML file, you should be able to extract the text in the HTML file. If it's a markdown, you should be able to extract the text. Now, you may ask, sometimes the markup may have context, may be important as well. So it's something to consider. But in most cases, extracting the actual text is preferred than storing it, as it is marked up or anything. Okay. So you look for tools that will help you to extract the text. Then after that, you normalize, right? Normalizing the information. So you can remove boilerplate things. Boilerplate are things that are repetitive, maybe just structural, they're not really important, right? In the document. And then fix Unicode errors. So Unicode errors are things like artifacts due to encoding. Then if it is from documents, you may also look at removing ads, menus, navbars, especially if you are getting this from websites or other documents on the web, right? So again, you have to write code that does that. Or you can use tools. There are a lot of tools that we can use, and we can look at some of them. Then expand abbreviations. If the abbreviations are domain specific, right? You may want to expand the abbreviations because the abbreviations help in adding more context, right? So it will help with the search. Then after that, we have what we call deduplication, right? Using sim hash, min hash, or embedding similarity clustering. Well, deduplication is where you may have parts of the text that are essentially similar, right? So similar that they're almost the same. Okay. So those are the steps that you take in the first part, which is data sourcing and pre-processing. Then the pitfalls, the things that may go wrong there, the embedded navigation is repeated on every page. So if there are a lot of websites that have navigation that is repeated on every page, right? So that may sometimes pollute the index, mainly because of the repetition, right? And difficulty to deduplicate. Then you have what we call OCR errors. OCR is optical character recognition errors that may affect retrieval quality. So this is in a situation where the data is kind of digitized or scanned from archives or from paper documents, and you're using OCR. So you may have situations where the characters are not properly recognized. So that will affect, of course, the retrieval quality. So we are now talking in a situation where you are building this for a very large, kind of audience, kind of for a corporate or enterprise, situation, right? For what we may be doing, we may use very simple, data so that we will not have a lot of these issues. But in real life, yes, you will definitely have to face some of these things. So that's why you have to be careful about them. So HTML extraction will include headers and footers repeated 1,000 times. So you must remove all of those. This is basically what we are saying. So that's a deduplication of parts of the whole thing. Then we have what we call chunking strategy. So when you are chunking, you have to ask yourself, how do I chunk? Remember, chunking is when you take this large body of text and you split it into smaller um, sentences or paragraphs or smaller sections, right? Each small section is what you will store in your vector database. So the chunking, first of all, is you have to ask yourself, what strategy am I going to use for chunking, right? Context quality is very important. You need to be able to maintain the context, right? The retrieval performance is also important, when you are chunking, and also minimizing hallucination likelihood. So these are the things that the chunking, if you do a good chunking, it will affect or forestall these things. But if you do a bad chunking, then you could have issues, right? So there are different methods that you consider for chunking. The first one is fixed length, which is like a baseline. Okay, you just say, okay, I'm going to chunk this based on 300 tokens. Every 300 tokens, I'll chop it off. I'll chop off the information and then use that as one chunk. Then I'll run again for another 300 tokens and I'll chop it off. So you basically chop off the information based on 300 tokens or whatever number you choose between 300 to 1,000, right? Now, of course, remember, first of all, that tokens don't necessarily translate to words. You can have tokens that have multiple words, and you could even have tokens that are, have incomplete words as well. So, that's a guideline. But the issue with the fixed length chunking is very easy to implement. You can just run code that splits it based on length of. You first of all tokenize the data, and then you just split it based on that, right? But the problem with that is, imagine if you were going 300, 300 or 400, 400, and you're not checking anything, and you chop off in the middle of a sentence, or you chop off in the middle of a paragraph, right? That particular chunk will now have half of the paragraph. Then the succeeding chunk will have the remaining half of the paragraph. You have basically split the context into two, right? So you're going to send the LLM. If you retrieve that one and send, you're going to send LLM an incomplete context, right? Half of a paragraph. So that will really reduce the quality of the generation of what the LLM is generating for you, because you did not complete the context. So we cannot just go with this simplistic fixed length chunking. So it's better we go with something that is more amenable or sensitive to the context, to the semantics. So you chunk at what we call semantic chunking. You chunk at semantic boundaries. So semantic boundaries are, you chunk at the end of a paragraph. You chop it off at the end of the paragraph. You chop it off at the end of sentences, right? So that you have complete context in it. So the benefit of that is that, of course, when you send that one, you have a full context. You don't have, your context being half of a paragraph. In fact, sometimes you can even say, okay, the body of text, right? What are we even talking about? If we're talking about the policy, maybe we should send the whole policy, right? So of course, how do you ensure that you sent the whole policy? If you are chunking and cutting off at paragraphs, you might have cut off the last paragraph of a policy. So how do you make sure that the next chunk also gets pulled in because it's part of that? So you can use an LLM for chunking, right? The LLM that you can even prompt the LLM to help you do this chunking and to chop off into sections based on word boundaries, topic boundaries, paragraph boundaries. The best is topic boundaries, because a paragraph, that boundary could be like it chops off a second to the last paragraph, while the last paragraph still holds the remaining part of that topic. So topic boundaries are the best, where you are chopping off, and the entire thing is complete. So sometimes if you're doing this kind of chunking, sometimes your chunks may be smaller and sometimes may be larger, but you can have like a mid value and say, okay, I want to chunk at 500, right? Tokens, but I would use some semantic wisdom, you know, so it can go above 500 or below, right? If I want to go above 500 and to get to the next topic boundary, it may exceed my 1000, then I can go below 500 to maybe 400 and chop off at some point before a new topic starts. So there are tools that you can do that. LangChain actually has a lot of tools. So you have a LangChain semantic splitter, and then Llama Index also has a semantic chunker. So we are going to look at how we use this when we want to do our RAG example. Then we have what we call hybrid chunking. So hybrid chunking is basically you are doing semantic chunking, but you cap it at a maximum token size, right? So what that means is you specify that this is a max token. So chunk it anyhow you like, but don't exceed this max token. So the hybrid chunking is really good for enterprise documentation with long sections, because sections can be so long, right? You don't want to exceed a certain max. Then we have what we call graph-based chunking. So graph-based chunking is an advanced kind of chunking where you, first of all, analyze the document and you create what we call a document graph using sentence embeddings. So you first of all do embeddings for for the whole document, for the sentences in the document. And then after you do all the sentences in the document, you now build a graph that kind of relates the elements, right? Relates those elements or those embeddings, which basically will form a graph. And then you create what we call overlapping subgraphs, right? So that's graph-based chunking. Chunking is an we may take some time to look at some of these strategies, maybe next week, right? In detail. Particularly chunking, because chunking is really very key element in this. So some of the considerations, right, when you're doing chunking is, first one is overlap, right? So always ensure you have some overlap, 10 to 20% overlap to cover boundary issues, right? But if you do overlap too much, then you are going to end up with a lot of duplication. So that will increase storage, right? And it will also increase retrieval redundancy. So for example, if you chunk in a paragraph, you can chunk into the next paragraph, right? For the previous chunk. And then for the next chunk, you don't start at where the previous chunk stopped. You go back maybe one paragraph before and start chunking it from there, right? You start chopping it up from there, so that the previous chunk will have a bit of will have the last paragraph, and the next chunk will also have that last paragraph. So that ensures that you kind of, the context can still be maintained, there's still some continuity in the context, especially when you are trying to assemble all of those things together. Then the other consideration is the chunk size, right? If the chunk sizes are small, then you have more pinpoint specific answers, but you also have to make more API calls to your vector database if you need to get enough context for for the LLM to make sense. But if you take longer chunks, right, from 700 to 1,500 tokens, you get richer context, because definitely, of course, you have more information in each chunk, but there's also a risk of having irrelevant information. So you have to now strike a balance between having smaller chunks and more records that you have to do more calls, or larger chunks, less records, but each record may have information that is not really relevant to the context that you want to send to the LLM. So after that, the next thing is, which model are you using for your embedding? And I think we talked about this already. So the embedding model choices, what are the things that matter? The dimensionality. We just talked about it now. whether we are going to use, 384 or 768 and all of that, right? That's what that matters. Domain adaptation, basically, in which domain was this trained, right? Because embeddings, the domain in which an embedding was trained actually matters. If it is far away or unrelated to the domain you want to use it, you are going to get embedding that does not really capture true relationships between the concepts that you are storing. So your similarity search may give you, this one is similar, but it's not really similar because the embedding model was not trained in that domain. So this is something you need to be very careful. So in the situation where you are using it in a domain that is not even that um, available, then you may end up having to fine tune the embedding model yourself. And that's something machine learning engineers would do, right? Multilingual needs, yes. Some embeddings can, some models can generate embeddings in different languages, right? Different languages, they'll still be able to generate embeddings that have meaning in each of those languages and across multiple languages. So that's a multilingual model. But there are some models that are not really multilingual. They were not trained, on different languages. So their embeddings in one language may be different from embeddings in another language. As a matter of fact, a very easy way for you to do language translation, which is what people used to do before, was you train models in multiple languages and they essentially have the same embeddings. So you can then generate embedding for a particular sentence in one language, find a matching, the closest match, and in another language, right? But of course, language translation these days are end to end, so you don't really have um, a lot of that, even though some still do that. Then the other thing is the cost per 1 million tokens. Both the cost of inference, right, in the LLM, right, the cost of inference in the embedding itself, and the cost of storage in the vector database. So these are all things that matter, right? So then latency is how fast all of this is happening. If you're using API calls, there might be a lot of latency. It will take more time. It will be longer, right? But if you're having it locally, yeah, you not have latency and maybe it runs faster. But then again, locally also limits the kind of the capacity of your model, simply because you know your compute locally is not strong enough. Okay. So the recommended models, right, in 2025. So take note of this slide, is for you to do your embeddings. You have OpenAI text embedding 3 large, which we saw that, and you can look at that as well. Then you have OpenAI text embedding 3 small, right? So you have best quality 3 large, 3 small is best price performance ratio. Then you have Voyage large 2, strong multilingual, Cohere embed version 3. Well, these are not all, right? Because like this is not exhaustive. There are so many models. I think you can just try as many as you can. So some of the considerations is text normalization should match embedded model expectations. So when you normalize your text, normalize in such a way that the model is gets what it's expecting. Then there's a difference between sentence embedding and paragraph embedding, right? Paragraph embedding is usually better for RAG. So choose embedding model that can do paragraph embedding. In other words, you give it an entire paragraph and it embeds rather than taking sentence and embedding sentence by sentence. Because the paragraph embedding, the entire paragraph makes more meaning, has more context than just cobbling together each of the same sentences individually in the paragraph. So we'll talk about vector databases. I think we've already looked at the options you have. Pinecone, we've looked at Pinecone already. So Pinecone has a lot of enterprise features, hybrid search, metadata filtering. We also have Weaviate, which is open source and is managed. I'll point you to that so you can look at it as well. We have Files, which we talked about. It's a local one. It's a library that you can pull in and install, and it runs well on GPUs. So if you have GPUs on your laptop, then Files would be nice, but you run it locally. Then Chroma is the one that has a very simple local store. That's the one we're installing now to see how it works. Then you have these other ones, mil views, or zillies, right? Then you have different index types. You have HNSW. Then you have um, you have IVFPQ, which compresses large data sets and lower accuracy. And you have a flat search, which gives you exact search, but it's really slow for any vector that is more than 1 million. If you have more than 1 million vectors in your database, then you can also filter the metadata as well. So it's not just by the vector database. You can also filter the metadata by the source, timestamp, section headings, doc type tags. These are all information that you will yourself add into the database, right? When you are creating each entry. So the metadata doesn't come from anywhere. It doesn't come from, the sky or space. You are the one that will create this metadata. So you have to also, selection of metadata is also very key because that helps you, to figure out, later on when you're trying to filter, it helps you to filter. Okay, so then the last part of this, well, not the last part, but the next part is retrieval. Retrieval is very important. You need to be able to retrieve the right context. If you don't retrieve the right context, you are going to have difficulty, right? So there's basic retrieval, which is just saying, okay, give me the top K entries, right? Or KNN, what we call K next neighbor, right? Give me the top N entries that match this vector that I just passed in, right? Which is what we just did. And you can normally take K from between 3 to 8. So if you take a K of between 3 to 8, right, you can then use that and send it as, the context, right? But there's also the consideration where you can do a re-ranking, right, using what we call a cross encoder. And there are tools that will help you to do that. Then you have advanced retrieval where you can have multi-step retrieval. So in the multi-step retrieval, the first step is create embedding for the query, right? Then retrieve the top 20 chunks that are close to the embedding of that query. Then you re-rank those top 20 using a re-ranker, which is a library. All of these tools like LangChain and so on that you use to make RAGs actually give you all of these abilities. Then when you rank to, again, the top 20, you now get the best 5, right? So you now pass this best 5 or the best 3 or best 4 to the LLM in addition to the query as the context, right? That's a multi-step retrieval. So the re-ranker is what it goes beyond just looking at embeddings because sometimes there could be errors or the embeddings are not perfect, right? They are really good, but again, like we said, embeddings depend on the embedding model. So a ranker helps to bring more context and fits more. A ranker is something you can even write yourself, right? Or you can use existing tool. So the reason why you can use a ranker at this point is that by the time you've taken only 20 chunks, that's a small amount of work to do. So you can easily do that with some kind of custom system. So after that, the next thing is query transformation. So you can use the LLM to rewrite the query, right? Expand it, generate synonyms, and create domain-specific search terms, right? So what this does is basically, if instead of just passing a straight up query into the embed, right? You can use LLMs to do that, to write the query. Okay. Both before or even after, right? After you've retrieved, you can use an LLM to do your prompt chain properly, or do the entire queries, right? Properly. You can also use LLMs to generate synonyms and create domain-specific search terms. Then you have a hybrid search where you can combine dense vectors with keyword search, like we said. So you not only search it within the vectors, you also search keyword search within the metadata, right? And then you have metadata filter, right? So this is the most robust method for very long documents because it really basically increases the relevance of the things that you are bringing, out from the database. Then we have what we call recursive retrieval, where you retrieve multiple candidate chunks for multiple generated queries, and then you fuse a ranked list. These ones are best for complex and multi-hop questions. And you have agentic retrieval, where you can use an LLM agent to basically plan retrieval of the um, the data from the vector database, right? So you can plan a search, retrieve, evaluate, and then retrieves again. So this one now this is necessary for what we call multi-document reasoning, where you have a lot of different documents. You can now see that we are using LLMs to even help with the retrieval as well. So these are a bit more complex, approaches. Then after you have retrieved the additional context, you need to construct it. So this is now prompt engineering, right? So you have prompt templates. You have a prompt template. It has to contain the query, the original query from the user. It has to include the system instructions. You can also include instructions for citation. If it has to cite policies for enterprise cases, it has to cite policies and all of that, right? So it has to basically do that. Then context blocks. Then you have to also give it the answer format, right? So we talked about all of this when we're doing the prompt chaining um, examples. So you are basically going to bring all of this. You can use a prompt template to do all of this, right? Of course, you have to assemble all of this context together into a single prompt, right? So this is an example. So look at this. This is an example of a prompt that you would write, okay? After you have extracted the information from the database to get this context, then you can say use only the information in the context, cite the context by section title. If the answer is not in the context, say not found in the provided documents. Then the query, this is now a placeholder, right, that you pass in the actual query. This is the query that came from the user, right? And then the context, this is now all the chunks, which you now stack them, one after the other, right? In the sequence, in the order of the ranking, either the ranking that came from the vector database, or if you did a re-ranking, the final ranking. And then the answer, this is how the LLM will respond to you. So this is like a very good, simple example of how you would, assemble the context along with the query, using this kind of prompt. So the considerations in this case, you have to put all the metadata, titles, headings before every chunk. So that's a good thing to consider. Order chunks by relevance, like I just said. Then use separators to prevent chunk bleeding. So in other words, when you are dumping the chunks into this placeholder, it's just talking about how you arrange the chunks. You can actually use separators so that the LLM will understand that you're actually using separators, right? And then you have to always take note of context window. So remember what we talked about, context window, context window. You have to take note of that. So once that is done, yeah, you push it to the LLMs, and there are so many LLMs that are recommended here for RAG, right? You can try them: OpenAI O3 Mini, O1 Preview, GPT 4141 Mini, Claude, Sonnet, Llama, but there are a bunch of others, right? Even these new ones that are coming in can really be good as well. Some considerations as well: keep low temperatures for RAG, because you don't want the LLM going off key, going to talk about things that are not in the context. Okay, so we keep very low temperature. Tune the max number of tokens based on the domain of the information, and then you use structured outputs, JSON mode, for predictable answers. So then you can do evaluation. So this is if you want to evaluate a RAG, right? You have what we call recall precision at K. So K being the number of chunks that you've eventually embedded into the final prompt, MMR gain, and chunk hit rates. So Those are the evaluation, retrieval evaluation, groundedness, faithfulness. Does the LLM cite context? Does it hallucinate? Compare generation versus source. And then end-to-end task success. When you give it a whole task, how does it do, right? Accuracy, completeness of the answer, correctness of the reasoning. Then you can use human annotators or LLM as a judge with constraints. So you can use human beings to annotate the result from your RAG to ensure that it meets requirements. Then we have guardrails and safety. So some of the techniques to make sure that the LLM does not hallucinate and start telling you rubbish. Some of the things that you see there, one is enforce citations, right? Enforce citations. Then the second one is tool use, enforce use of tools. So a tool is basically a function that you can give to the LLM and tell it how to use it. We are going to talk about tools later on down the line, right? Then refusal generation, right? So is it able to generate refusal when it doesn't have information, or when the information you're asking it or what you're asking it to do is not correct? So we did an example of that at the beginning when we gave it some kind of boundaries and guardrails and said, okay, if somebody speaks words that are in this particular list of censored words, don't speak, right? Well, right, what we did then was we were basically redacting the words. But the other thing you could do is you could actually instruct the LLM and tell it, don't speak those words, right? Rather than redacting it after the LLM has spoken them. Then, so sensitive data filter, that's another thing. Per source permission checks and rate limiting, abuse protection. So these are things to consider if you are building the service. Then guardrails, you have models that can, do guardrails. Guardrails is basically the kind of prompts, system prompts or developer prompts that you give to the LLM to prevent it from going outside of the safety boundaries, right? And you have to define those safety boundaries, right? So, and there are examples of models that can help with that, guardrails AI, open AI moderation, and so on. Then scaling is also important, right? If you're going to run RAG for a large number of users, large number of hits, and so on, you have to consider latency. You can catch the embeddings so that you don't need to call embedding models for every single one. If you already have embeddings, like if somebody is typing in a sentence that has already been typed in before, you can just go look for that sentence, right? And pull embeddings that have already been cached instead of asking the LLM to, sorry, the embedding model to generate another embedding, right? Warm re-ranker, re-embed frequent queries. So if there are a lot of queries that are very frequent, you can re-embed those ones. Use re-ranking only when needed, right? So we talked about re-ranking only when needed. If, for example, the number of matches are so much and the ratings of the matches are so close together or something, right? So you can define criteria that you use to decide, when to do re-ranking. Okay, indexing, incremental update. So this indexing that you do in the vector database, you always have to do updates. If there are new information that come in, you have to make new entries into the vector database. You have to make new offsets. That's what incremental updates mean. You can rechunk again, every night, and then you have version documents. So as documents continue to change, right, you can rechunk them and reinstall. Then we have memory and storage, right? So compression, port sizing, sharding. So there are some of the choices that you can make, architectural choices. So the first one is you can use an internal knowledge base or enterprise search, right? So you can have a hybrid search, right, that has vectors in them. You can strongly filter by metadata. Long chunk sizes, you can choose longer chunk sizes, and then query rewrites. So this is architectural choice. If the use case is an internal knowledge base, for a big enterprise, that's why you're using long chunk sizes. But if it is RAG for coding, right, you can embed the code and then you create embedding of the AST nodes. AST is basically a tree of the code, the code structure, basically a search tree of the code structure, right? So that's an AST. So you can also do embeddings of that. Then you can chunk by function or class. So that one is kind of clear, right? Because those are the semantic boundaries for code. Then you can re-rank using code-specific re-ranker, right? Then you can restrict the LLM from guessing the missing code. So this is for RAGs that you want to use for coding applications. For a research assistant RAG, you can multi-hop reasoning may be required because you want it to be able to jump to other parts of the document, multiple documents, multiple page documents, and still maintain the context. Then you use agentic retrieval because just straight up retrieval may not be enough. So you have to plan because it's a lot of documents and the documents are related and the relationship is across multiple documents. Re-ranking is essential if it is a research assistant. And it's better to use small chunks, maybe 200, 300 tokens. Then if you are doing a legal or policy RAG, right, then you have to have precise citation. So your query has to include that it should give precise citations. It needs to, and when it's doing citations, it will do the citations based on um, the sections of the document that it is citing, the section, the chapters, and things like that, right? You have to have strict guardrails in legal because you cannot let the LLM hallucinate, okay? And then your answers need to be structured and you need to be able to chunk by section and article. So I think those are all of the considerations when building RAGs. So when you put it all together, right, what you have is, first of all, ingestion, which is when you are pulling in the data initially, right? You do text extraction, you do cleanup, you do semantic chunking, you embed each chunk and you store in your vector database. That's the first step. Then when you are querying, the user brings a question, you normalize the question. Then you can optionally use a large language model to rewrite that query in such a way that maybe it will be more effective in retrieving the necessary context. Then you can use a vector plus keyword search, right, to get the top 20 matches, right? Then you can re-rank those top 20 to top 5, and then you can inject those top 5 into your prompt and make sure that when you're constructing your prompt, make sure that you have added all the necessary context, right? And also when you are dumping the chunks into the prompt placeholder, the prompt template, ensure that you separate the chunks with a clearly defined separator. Then after that, the LLM will generate your answer and include your citation. Then you can do an evaluation of that and improve the process. So that is a summary of how you would build a RAG, right? Now this is for really high level, this is really high level, um, you know, enterprise grade, enterprise level RAGs, right? But it's good to know this. Now we're going to do hands-on, and with the hands-on, you are just going to do a very simple RAG. But of course, we've run out of time, so we'll not do that today. But I'm going to give you some guidelines, and your task for next week, not for this week, would be how you can put together a RAG. I'm going to give you the code sample of existing code sample based on these principles, right? Of how you can do all of this, right? So that's it. That's it. That's how we build a RAG. I will also give you pointer to Chroma, but I would advise to try it on your own, right? I'll send you videos as well that you can watch to give you additional knowledge. So that's all from me.